What's going on? Okay, can everybody hear me all right? Yeah, it sounds like the mic's on, right? Perfect. All right, yeah, so I know everybody is kind of wrapping up lunch, so hopefully this talk should be pretty accessible, and I tried to make it a bit high level since obviously people are coming out of lunch and I'm expecting to get, somewhat divided attention, so hopefully it's interesting. It's a bit about who I am. So my name's Sam Foreman. I'm currently an associate computational scientist in the data science group at ALCF here. So my background is in high energy physics, specifically lattice QCD, and I work with James Osborne and Xiaoyang here on lattice methods. And so that's my background. My PhD was in high energy physics. Since then, I've kind of transitioned a bit maybe to working more on machine learning methods specifically and scaling. Most of my recent work has been on scaling large language models, but I've also been working on large-scale distributed training more generally, and efficient workflows on ALCF systems. So for those who might be interested, there are links here with additional links that you can read more about if you're curious. So also I sent the link to these slides are online in the Slack channel, so people can follow along if you want, and easier to access the links and so on. Right, so today I'm going to be talking about the kind of high-level overview of large language models, and specifically how we have been running and working with them on ALCF systems. So as I'm sure probably everybody is aware by this point, large language models are the hottest new topic, really all the rave at the moment. Here's kind of just a GIF that I stole from this awesome LLM repo that shows how different capabilities seem to emerge at different model scales. So this is obviously, qualitative, but this is kind of the general idea. We've seen as large language models have scaled to larger and larger parameter counts with larger and larger models, they tend to have these emergent capabilities. So things like, it just went away. So things like translation and all of these kind of higher level complex features seem to be emergent at larger model scales, and is kind of a new behavior that people are kind of working to understand and get a better feel for. So you can see this also kind of quantitatively as well by looking at the accuracy or quality score for different, as a metric on different tasks. So modular arithmetic, word unscrambling, so on and so on. There are all these sort of evaluation benchmarks that we can use to evaluate a model's performance. And what I'm trying to illustrate in this graph, actually maybe this is, I feel like I'm a bit too short for the mic, and I move around a bit more. So really all I'm trying to illustrate in this graph is you can see at different, so at some model scale, a lot of these graphs seem to have this kind of inflection point where their accuracy on a given task grows tremendously. And so this is kind of representative of this emergent capabilities that I was talking about before. So how do we get there? How do these capabilities come to emerge? And so I guess going back to 2018 was kind of the first major production releases of these large language models. They're a far cry from what we have today, but they were the first kind of, push in this direction. And since then, the types of architectures, releases from different companies, variations on model parameters, count, data sets used to train with, and so on has kind of exploded. And you can see here that it branches off pretty early between decoder only and encoder decoder architectures. And so this is a battle that's still kind of, ongoing, but those are the kind of two major types of large language model architectures. And so as you can see here, a lot of this has been dominated by commercial enterprises like OpenAI, Google, Meta with the Llama codes, or with the Llama language model series has also been very popular. And really all of this is just to say that there are a wealth of different large language models out there in the world right now, and different companies and people working on them at the moment. So this is a slide that includes a table with various recent results. So going back to 2017 with the original Attention is All You Need paper, and kind of includes, going through in time, so kind of sequentially between 2017, so on and so on, to the present day. This is kind of just an aggregated list of some of the important works, papers that have really kind of made an impact on the large language modeling research community. So now maybe to give maybe a bit more detail for those who might be completely lost or unaware of how these large language models work. There's kind of multiple different stages of the path to deployment. So the first step, and what actually ends up taking up a lot of time, is this data collection and pre-processing step. So this is actually very important. So we've learned over time that this is actually one of probably the most important steps. And it seems to be the case that language models trained on high quality data sets typically, I want to be careful about what I say. There are a lot of problems with large language models that have been trained on the internet at large. Obviously, there's a variety of bad text or things that we wouldn't want an agent out in the world to be kind of spewing forward, and kind of, there are a lot of possibilities for misuse for large language models, and one of the largest contributors to that can be the quality of the data that they're trained on. And so that's a part of a much larger problem, but this step of data collection is actually pretty important, and will continue to be more important as we try to adapt and modify large language models for scientific use cases. Even working with scientific data is not as straightforward, and trying to develop and come up with methods for dealing with that is going to be important, definitely in the coming years. The next stage, once you've got all your data cleaned, ready to go, is what's called the pre-training stage. And so this is what actually ends up taking up the bulk of the compute resources. So there are a lot of decisions that need to be made before starting this long, kind of arduous pre-training process. So things like the model size, architecture, the parallelism strategy that you want to use, learning rate scheduling, all of these kind of generic ideas from machine learning in general become even more important when you are planning a 6-month, when you're planning a 6-month training run that you anticipate to use all of your available compute resources. You really want to make sure that you thought out these decisions ahead of time and aren't, halfway through realizing you made a mistake and needing to start over and wasting all of this compute. And so things like that happen, obviously, but trying to prevent that as much as possible and being kind of, thoughtful in how you design these types of things can save time in the long run. And so this is what I will probably be focused most on today, and is the part of the process that I am most familiar with or have the most experience with. But once you have a pre-trained model, so these are what are typically deployed from Hugging Face or the Llama code releases and so on. Those are what are called pre-trained models. So Google or Facebook or somebody puts in all this work, trains it for months and months on end, and then they release it on the Hugging Face or wherever else. And then you, generally as a researcher or user of these language models, if you were to want to, could download that pre-trained model and fine-tune it on some specific data set or for some specific use case, whatever the case may be. And that's kind of a variation on this pre-training, but is really at the end of the day, the same basic idea. It's, you freeze the bulk of the weights and have some head at the end that you leave trainable, and you essentially only train the last few layers. But at the end of the day, the supervised fine-tuning is just another variation on the training process, although it typically starts with a pre-trained model. And so then after all of this, once you've gotten your model and you're happy with how it works, you then would have to deploy it out in the world. And this is it comes with a whole other wealth of challenges, maintaining deployment, making sure that your model isn't, spewing racist garbage. The whole, that's a talk for another day, but that's a whole another part of all of this that is actually pretty important, especially for people wanting to put these systems into production. So this animated illustration here kind of shows how this pre-training process works. So it takes in a sequence of tokens and works autoregressively, essentially, to try to predict the next token. Depending on whether or not this next token is the token that we are looking for, there will be some error that gets backpropagated. There will be an error in the loss term. You can evaluate that to backpropagate the gradient updates through the network. And the training beyond that is kind of, identical or similar to anything that you've seen before. So then, I guess this is another kind of graphic. This is what I was getting at before as well. So once you have a pre-trained model, typically what we do is you want to fine-tune it to be better at some certain task, or you have some data set that is, very custom to your use case or whatever you want to look at. And you can fine-tune a pre-trained model on your data set, or in this case, to be better at a certain task or whatever the case may be. And this is a less compute-intensive process generally than the process that it takes to, completely get the pre-trained weights. But this is actually becoming as language models are being deployed out in the world more and more people are wanting to adapt them to their own certain use cases. And that is done by fine tuning. And so this is becoming also kind of an increasingly important part of this workflow. For the sake of time, I probably won't go through this too much, but I'm sure this is a diagram that anybody who's worked with or seen large language models before has seen at some point. So this is the basic network diagram of the transformer architecture. So you take as input some sequence of tokens, it gets fed through these series of layers, and then we can compute a loss relative to the outputs, which are just the inputs shifted by a token. Yeah, that's really all I want to say about that. Another kind of nice graphic, hopefully, since we're coming out of lunch, to give you an idea of how all of this works. So you take as input some token or some series of tokens, in this case, the quick brown, and you want to try to predict what the next token will be. So you pass this input through the series of layers in your network. It spits out this array of probabilities. So you will have one probability for each item, each entry in your vocabulary. So for the English vocabulary, that would be just, the set of all English words. And it will predict the probability that each of these words in your vocabulary is the next token. So for example, you can see the probability that the next token is aardvark is 001, whereas the probability that the next token is fox is 0.9. And so with that being the most probable next token, we can assign that to the next token, and oh no. Oh, there's supposed to be another illustration here. There it goes. So you can see how this works. So just as before, some input series of tokens gets fed through the model. It will output the next token, which you can then feed back into your prompt and use that kind of autoregressively to generate, sequences of whatever length you may want. There are other methods for doing this. So this method shown here kind of does a greedy selection, where it will always pick the token with the highest probability to be the next token. But you can imagine some sort of you can introduce stochasticity into this by for example, selecting the top 3 most likely outputs, or whatever kind of variation on that. But that's kind of the basic process. You take as input some series of tokens, use that to try to predict the next token, and then kind of use that to, oh no. All right, thanks for bearing with me. So So I should go, what time did I start? I should wrap it up at probably about 1, right? Yeah, sound about right? Okay, just trying to keep track of time. So that's kind of a very high level overview of how large language models work, and the kind of the different stages associated with pre-training and deploying all of them. But since this is the ALCF Hands-on Workshop, I figured it wouldn't be fair to leave you guys without going into a bit of the details. And so this is the area where I have the most experience, and so it's just what I'm most familiar with. And that is specifically looking at different parallelism strategies for efficient training. And really, so there's just a quote that says, modern parallelism techniques enable the training of large language models. And this is really pretty true. The growth and scale that we've seen for large language models, architecture sizes would be more or less impossible without current parallelism strategies. So by taking advantage of all of the parallelism strategies available in DeepSpeed, for example, can reduce can take your training time from what would otherwise be on the order of 6 months to, in just a few hours. By doing efficient parallelism with, enough GPUs, you can really parallelize things pretty efficiently, which has the impact of, significantly reducing the amount of compute that you need to spend on training. So I guess some of the morning talks already kind of covered data parallelism, and I think Huiho actually briefly touched on tensor parallelism. And so the details of this, again, aren't probably too relevant unless you, like me, are also interested in training large language models. But it's kind of these techniques or these kind of ideas carry over to machine learning and distributed training more generally. So while they might not be their use in the context of large language models might not be directly applicable to your research, but the concepts of model sharding and efficient parallelism, I would imagine, should be. So in the data parallel scheme, this is probably the most common, where you maintain identical copies of your model on different workers, and each worker receives some subset of the data at a given time. At the end of the forward pass, all of the workers kind of sync up and communicate. They do an average of the gradients and then backpropagate those averaged weights. And this is probably the most naive, but is also probably the easiest to get set up and get going with. More complicated than that is what is called tensor parallel or model tensor parallel. In this case, you split tensors up into multiple chunks that get split up across the GPUs. And in order to complete the forward pass, different workers take and grab what they need from different GPUs, and this kind of gets orchestrated into a pipeline that helps to alleviate the memory pressure. So if you have another big part of all of this is that as we want to try to increase and scale up to larger models, we very quickly run out of available memory. And so one way around that is to divide up the work add back in a trade-off between communication and computation. So I can free up GPU memory at the cost of having to get the parameters that I don't have anymore from my neighbors, whoever they may be. And so there's really this kind of I don't really love this diagram, but this seems to be the only one that, I don't know, is out there that illustrates these offloading and parallelism techniques. So in the most naive case, you can offload all of your optimizer states, and basically workers will get what they need from the rest of the workers as needed. And there's this kind of, handoff of weights that happens during the forward pass. Yeah, maybe the details of this probably aren't worth getting into much more detail. But you can see here in this baseline case, I don't know how well you can see, but there's a very thin blue line and then a very thin orange line followed by a much bigger green block. And so the blue line represents the GPU memory taken up by the parameters. The orange line represents the GPU memory taken up by the gradients. And the much bigger green block represents the memory taken up by the optimizer states. And so in the most naive case, which is I think 0-1 data parallel, they call it, deep speed calls it, we offload the optimizer state. So now you can see that each GPU only has some fraction of the optimizer states. And so in order to compute the forward and backward pass correctly and completely, it will need to get all of the optimizer states that it's missing from the different GPUs. And so there are mechanisms for kind of setting all of this up and synchronizing communication. And the details are definitely beyond the scope of this talk, but it's I think, pretty interesting and is definitely an active area of research. Yeah, again, this just goes into tensor parallelism. This is kind of another diagram that shows how this matrix multiplication, when broken up and done in a column parallel fashion, is identical to a different way of multiplying them in a row parallel fashion. And so depending on the sizes of these different matrices, this might have different advantages or disadvantages. Again, this is a diagram that's probably much too complicated to take anything away from in this 20-minute talk. But this is kind of the maximum achievable parallelism. So in this example, you can imagine having data parallel. You can imagine having multiple copies of data parallel ranks, so this top gray box and this bottom gray box, that are communicating through some zero data parallel offloading communication like we saw on that last slide. And within a data parallel rank, you then split it up even further. So you have multiple model parallel ranks. Those can be split across multiple pipeline stages. But again, this is probably maybe a bit too low level. Another way of kind of visualizing this is looking at what subset of parameters each GPU has. And they really put an emphasis on trying to break it up into 3 different dimensions here. So you can see in this example, you would have like GPU 0 and GPU 4 communicating through some zero data parallelism, and going between 0 to 8 to 16 to 24, you would have some pipeline parallelism. So that would be what these pipeline stages are. But really, all of this is to say that there are a lot of different mechanisms and utilities that you can use to improve the communication between all of your different workers that are participating in your training, which is obviously beneficial since you want to spend as little time as possible communicating and as much time as possible running the actual computations. So it has that advantage, as well as giving you a mechanism for freeing up memory for larger models, essentially. So by offloading these parameters, either between different GPUs, or there are also mechanisms for like offloading to NVMe or flash storage. And so in doing that, it really allows you to scale up and continue to push for larger model architectures. And in doing so, then you hopefully get these emergent capabilities like we saw earlier. Okay, so that was a long-winded explanation of the different parallelism strategies. And all of that was really background or an introduction to kind of how we think about these things here at ALCF, and what kind of performance considerations we take into account when trying to develop a framework that users can use, as well as for our internal research. So it's kind of this trade-off between something that is easy and accessible for all of you and for our users to use, and something that we kind of have internally that allows us to perform evaluation metrics and get profiling results for these distributed pre-training setups like I talked about earlier. And at the moment, there is this effort from DeepSpeed called Megatron DeepSpeed. And so this began originally as a fork of NVIDIA's own Megatron LM, which I believe at the time was probably had the most advanced functionality in terms of parallelism and low-level CUDA optimization. So that was another big draw. Obviously, it being developed and released by NVIDIA, they put a lot of work into low-level optimizations and really put in effort to make sure that things worked and ran efficiently. And so then Microsoft, wanting to build off of that success, created this Megatron Deep Speed repository, which the goal for which being that to kind of take in the best of both worlds. So having the advantages of deep speed and the zero data parallelism and all of the various offloading techniques that are built into deep speed native, while also being able to take advantage of all of these optimized CUDA libraries and low-level optimizations that NVIDIA had put into their Megatron LM. And the result of that is this Megatron Deep Speed repo. So it's originally from Microsoft, but we have been maintaining a Argonne LCF version that has some helpful utility scripts that help to simplify the process of getting started and working with and using these. So otherwise, it's identical to the Microsoft version. And I have included here, so I probably won't. It's probably not useful for you guys to watch me step through shell commands, but I've included here the instructions needed to go into the directory, set up your conda module. So this, as people have probably, so anybody who's tried to run things in the last few days has probably heard or seen that we haven't recently released a new conda module on Polaris. So this 2023-1004. And so this is using that newest conda module. And as of this morning, has been tested and working. So this, you guys really should be, completely free to go in and try to run this, play around with things, look at all of the code, figure out what sort of different, variables you can specify. So here, for example, this goes through all of the setup. And then to actually launch the training, you can specify things like the sequence length, the micro batch size, sequence parallelism type, the model architecture size, and so on. And so there are a bunch more settings that are specified in here that I'd be happy to talk more about if anybody's interested, but feel free to look through and hopefully it should be somewhat explanatory. And then finally, there's this ALCF train GPT3.sh. And so this, that shell script will, so if you launch it, this is what it'll look like, running that, specifying the model key, and then launching the training. You'll see some output that looks kind of like this. Should start off like this, and then there'll be a bunch more text. And then it'll keep printing text for a while, and then finally it'll stop, and it'll say something like, writing logs to yada, yada, yada. To view output, tail this log file, i.e. tail, and then the path to the specific log file. So you can watch the output as it runs by just running some tail command on that log file. And you'll see, hopefully, if everything works as expected, you'll see something that looks like this. So job started at so on and so on. And then it'll have a bunch more information about how the run actually progresses. So I'm looking like I'm at about time. So these are additional details that actually shouldn't be relevant now. So when I had made these slides originally, it wasn't clear how we were going to have users try this out. And so I had initially anticipated everybody on their own needing to go through this kind of complicated and arduous install process. But as of this morning, I kind of abstracted all of that away from you, and you guys can now just go into the directory, load the conda module, and activate this pre-made virtual environment. And so anybody who's interested in the details, it's all here, but hopefully you shouldn't have to do any of that. So there are some additional dependencies that, again, as I said, are in that virtual environment, but if you're interested in the details and what it actually takes to work, it requires optionally flash attention. This Easy Peasy is a library I'm working on, and Apex, which is in the most recent conda module, but if you're trying to work off Theta GPU, for example, you would need to build this yourself. Although comes with an asterisk because that's also in the process of being simplified and made easier for all of you guys to use. Here, just more details about what each of these different scripts do, some additional environment variables you can use, again, more detail on what all of these scripts do. So this is train GPT3.sh is the main entry point for training. So this will explicitly go in and source all of the rest of these, setting environment variables as needed, and essentially do everything that you need to launch the process. So internally, it sources all of the rest of these files, and then at the end of the day, calls some MPI exec across all of the GPUs available, Python 3, this main pre-trained gpt.py file with some additional arguments. I guess, so I'm out of time. That's really all I wanted to say anyway. Happy to talk more about this. Anybody has any questions, thoughts, comments, I'd be more than happy. So I will also be one of the work organizers, coordinators for the afternoon breakout session. And so would be happy to talk about this in more detail if anybody is interested. Yeah, I think that was all I wanted to say. Oh. So skipping through the slide that I won't present onto the links, references. Yeah, I'll leave this up, acknowledgements. So yeah, sorry, thank you.
Thank you. Do we have questions for Sam?
Thank you. Hi, a really nice talk.
Oh, thank you.
I'm very impressed. Well, I have 3 questions. One, are you using weight and bias?
Yes. Yeah. So I am and have been. So I am a big fan of weights and biases and use it pretty religiously. But in the process of getting all of this set up in the virtual environment set up this morning, actually, trying to think about how to say this without. There is a kind of subtle, low-level, I'm reluctant to say bug, but issue maybe on Polaris that's related to forking a process using Python's multiprocessing that can cause multi-node runs to hang, and is obviously then very difficult to debug. And so in doing that, I disabled the weights and biases functionality from the repo at the moment. Right. But yeah, if you look in the repo, it's currently commented out. But if you were to want to use weights and biases, all it should really take is uncommenting out this.
Got it.
There's I think that should be commented in the main version, but yeah, so it should, I use it and it should be supported, but is currently disabled. So if you try to run it.
Got it. Thank you. And the second question is, what is so NVIDIA Apex has been, when it was first released, it has a lot of, fusing of batch norm or half precision. What is the use case now? Why it depends on that?
So to be honest, I'm not entirely clear how it's being used so to my understanding, I think it is being used to, at runtime, compile these fused kernels so things like fused I think there's like upper triangular softmax and a couple other fused kernels that I think that use it. But I'm not incredibly familiar.
Got it. I think later on, a lot of them built into the PyTorch, but there are some of them left over, so I have no idea where the boundary is.
And it's hard. Not only hard to keep track of what lives where, anymore. But so as part of this, we've been working with the Deep Speed team at Microsoft. And as part of that collaboration, they have done work to build some, new fused optimized kernels. And so I don't know how much that pulls in the Apex dependency. But yeah, that's a good question. And ideally, you would use that as little as possible.
Yeah. So the last one is, if you have time, maybe you can put say a few words about your package, easy peasy, what that does.
Sure. Yes, I would love to actually. Sure. So. This is something I've kind of been working on. So as I'm sure many of you are familiar with, it's not always terribly straightforward to launch and set up distributed training. So this is kind of a little library I've been working on that is tested and is confirmed to work at ALCF, so across Data GPU and Polaris. It also should work on Perlmutter at NERSC. And so this is kind of how I imagine, or you would use it in an application. There's this easy peasy .setup torch and setup TensorFlow. And so you could imagine, putting this in some condition, if I specify my framework as PyTorch, there's this setup torch function, which takes as input a backend. So this backend can be either DDP, deep speed, or Horovod. And the port optionally you can specify. If you don't specify it, it'll just get set automatically. And so this little function will take care of all of the complicated process of ensuring that the master host and master address are set and propagated to all of the workers and so on, and really do everything that you need to get set up for distributed training or multi-node use with PyTorch. And then similarly for TensorFlow, since there's only Horovod, it doesn't take in a backend. But basically, if you were to put this at the top level of your application, you could then launch it with any combination of framework and backend that you might want. So launching just using MPI exec on Polaris, for example, across all of my GPUs, specifying, for example, PyTorch and DDP. You can see that it, correctly initializes all of the. So this is on 2 nodes of Polaris, so it would be 4 nodes on one GPU and 4 on the other. And so you can see PyTorch DDP, deep speed's a bit more, and they have print out a bit. They're a bit more verbose. They print out some stuff internally. PyTorch and Horovod, and so on and so on. So there's still a work in progress. So that's why I was maybe a bit reluctant to advertise it, but yeah, it's ongoing. And if anybody thinks this is interesting or like to talk about that more, I'd be happy to as well. Also now almost 10 minutes over.
Yeah. In the interest of time, let's thank Sam again. And if you have any more questions, I think you're around for the breakout sessions, right? So, yes.